Today, we'll learn about shift register. Okay, for register, maybe you already know, right? For example, let I use D flip-flop. Maybe 1 D flip-flop, 2, 3, and okay, maybe 4 D flip-flop. Okay. If this D flip-flop use same clock connect together, that means when clock tick, when clock tick, all flip-flop will read data, right? Will read data from its input at the same time. Namely, it will load, right? Load data to update, okay? The output of each flip-flop. For example, if the initial value of this is A, B, C, and D, that means when clock tick, this flip-flop will read data from D, and C, the data is A. So when clock tick, Q will update to A, and this one update to B. This flip-flop become C at the output, and this one is D at the output. Okay, this kind of behavior is called load, right? Load. Okay, read data multiple bit at the same time. Okay, or sometimes we said this like parallel input. Okay, read multiple bit at the same time. Okay. Okay, now what happens if I connect this output to the next input, connect this to this, connect this output to next input. Okay, what happened? And don't use this one, don't use this one, and don't use this one. Okay, now if the next clock tick, the data at here is E. So what happened? When clock tick, what happened? This one, this flip-flop, you see data at here is C, right? And this one, the value at here is B. And this one, the input is A. And this one, read the data from E. So when clock tick, the new value of this flip-flop then become C at here, B at here, A at here, and E at here, right? So you can consider that the data is shifted, right? And the value shift from A to B, B to C, C to D, right? So it shift them is become A at here, B at here, C at here, and read data from this update to this position. Okay, so you know that the data is read only single bit. This kind of behavior is called serial in. Okay, and this kind of configuration is called shift register. Okay, it's register that and this flip-flop will read data from the previous register. Okay, So if you see the behavior, maybe if I write something like this, D C B A, okay, write something D C B A. Then when clock tick, right, C move to this, so C shift to this, B shift to this, and A shift to this, right? And input from outside, external input, okay, and replace at here. So you can see that the behavior become like that, a 1-bit shift, right, to the left hand side. So sometimes it's called shift left, shift left, okay, shift left. Okay, now you know, okay, about chip register. Okay, some keyword that you should know is input, output, serial, and parallel. Pretty easy, right? Okay, for input, for example, this is circuit of the system. Okay, this is input, right? And output. Okay, for serial, for serial in, the system will read data only 1 bit. Okay, only 1 bit. When clock tick, read data only 1 bit. When clock tick, read data only 1 bit. This is serial in. And how about parallel in? For parallel in, when clock tick, the system read multiple bit input. Read data multiple bit at the same time. Okay. About the output, if you use output only 1 bit when clock tick, okay, only 1 bit, okay, out. So this is serial out. But if you use something like this, multiple bit from the output, it's called parallel out. Okay. So the register, maybe have serial in, serial out, parallel in, serial out, serial in, parallel out, and parallel in, parallel out. Okay. So the basic configuration is something like this. For serial in, serial out, and as I already showed you that for chip register, this output connect to next input, okay? And this one connect to next input, and so on. Okay. So when clock tick, the data from serial in from this, okay, we update to this position, and this data will update to this one, and this data we update to next and next. Okay, so if you read data only 1 bit, it's serial in, and if you use only 1 bit output, it's serial out. Okay, very easy. Okay, and how about serial in, parallel out? For serial in, parallel out, you can connect something like this. Actually, it's the same. It's the same connection between flip-flop. The difference is output. For serial out, you use only 1 bit output, but for parallel out, you use multiple bit at the output. You use all output from the flip-flops. Okay, now for example, let I add more flip-flop right here. Add here D, Q. So totally we have got, for example, 1, 2, 3, 4 flip-flop. So we have got 4 bit at the output. Okay, now let's consider If at the beginning the value of this something unspecified, and the value A applied at serial in at this flip-flop. When clock tick, it does read A update to here, right? So it become A at here, and it is read some unspecified value. This one also unspecified, this one also unspecified. For the next clock tick, if the next value at serial in is B. So now this one, see, this is unspecified, right? And this one is unspecified, this one is A, right? And this one, the input is B. So after clock tick, it become unspecified, A, and then B, right? And the next clock tick, input is C. So now this one, see this one, right? Unspecified. This input is A, this input is B at the clock tick. So when clock tick, every flip-flop update the value from the input, right? So it become unspecified, A at here, B at here, and C at here. And for the next clock tick, the input is E. So what happened? Again, this one read data from A, right? And this one read from B, this one read from C, and this one read from D. So when clock tick, the new value is A here, B, C, and D. Okay. So note that if you use parallel out, your input apply in serial in 1, 2, 3, 4. Okay. You must wait for 4 clock ticks. So then you can use 4-bit output at the same time. You must wait for 4 clock ticks. That means this circuit, you can apply it as serial to parallel. Serial data, okay, convert to parallel output data. Just some application. And for this one, for serial in, serial out, if you connect this one, for example, 4. So when you apply input A here, you must wait 1, 2, 3, 4, right? 4 clock tick before this input, okay, go to the output. So you can use or apply this serial in, serial out chip register as delay, okay? Delay circuit to propose the output with some clock tick. For example, if you use 4 flip-flop, so you wait or delay by 4 clock ticks, okay, before this data will go to the output. Okay, now next, how about parallel in, serial out, and parallel in, parallel out? Actually, this circuit and this one is the same. Okay, the difference only 1 bit output or multiple bit output. And actually, this circuit you can use for serial in, serial out, parallel in, parallel out. Okay, all mode of chip register. Okay, now let's consider how this circuit work. Okay, at this part actually is marks. Okay, marks. Okay, or multiplexer. Do you remember this one also? Okay, now let's consider if I connect this one. Okay, then there are 1, 2, 3. Okay, for example, 3 bit. chip register. Okay. Now the mode depends on the signal at here, load or shift. If this one is 1, so what happens? This output is 0, right? So 0 and something is 0. Okay, this is 1, right? 1 and 1D. Input 1D, then it's 1D at here. 1D or 0 is 1D. So that means now the data from external input is feed, okay, and wait at this input of the flip-flop. Similarly, for this one also, data from 2D, okay, flow and wait at here. And this one also, ND, flow and wait at here. Okay. After that, when clock tick, okay, all of these flip-flop will read data at the same time and upload, okay, and update, okay, and the data, okay, from this one. So you can say that it's load, right? It is load, okay, read data, okay, read multiple bit data at the same time. And if we use multiple bit output, so then it's become parallel in and parallel out. Okay. Now what happens if I change this one as 0? This output of inverter is 1, right? 1 and 0 in is 0 in. This is 0. This output is 0. That means 0 or 0 in then becomes 0 in. So this flip-flop, and data from 1 bit of 0 in, okay, flow and wait at here. And this one, how about this one? Is 1 at here, right? And 1Q. 1Q. So it's 1Q at here, and then become 1Q at here. Okay, because this point is 0, right? Become 0 at here. And so on. Okay. This one also. This output then feed to the next input. That means when clock tick, this one read data from 2Q, this one read data from 1Q, and this one read data from 0 in. So when clock tick, data will shift to here, right? 1Q and 0 in. So this one is shift mode or 0 in. Okay. And for the output is parallel out. Okay. But if you use only 1 bit like this, so it's become 0 out. So you can apply this one as 0 in, 0 out, 0 in, parallel out, parallel in, parallel out, or parallel in, 0 out. Okay, and use all of this. So we're going to show example for medium scale integrated circuit of chip register. The first one is 164. This one, okay, is 8-bit chip register. Okay, the input that shift from this to this, okay, is from this serial A, serial B, and together. The output of this AND connect to input of QA, and QA connect to QB, QB connect to QC, and so on. That means when clock tick, okay, data will shift this direction. QA to QB, QB to QC, and so on. And for this chip register, this one 0 out, zero out, and it can use as shift mode or load mode. If you use shift mode, the data will read from serial input. But if you use load, the data will read from this 8-bit input A, B, C, D, E, F, G, and H at the same time. Now for this one, there is this clock inhibit. What is it? For clock inhibit, operate something like this. If this clock inhibit is 0, this is clock. High, low, or 1, 0, 1, 0. 0 or 1 is 1, right? 0 or 0 is 0. That means the output of this is same value of this one. For this one, there is one input, active low at the output. So the output then become 0, 1, 0, 1. Low, high, low, high. So there is a positive edge or negative edge at here. That means this signal can use as clock to take this one. But what happens if clock inhibit is 1 all anything is 1, right? When invert, then it becomes 0. So it's constant level, no clock edge. So that means no clock tick to apply to this flip-flop. That means this clock cannot tick this one. For this IC 166. Now let's look at here. Look at 194. This is universal chip register. For this one, you can select 4 mode as this one, as this function table. Hold, chip right, chip left, and load. You can select by apply 2-bit at S1 and S0. If S1, S0 is 00, it's not active, both. It's hold mode. That means after clock tick, the value at QD, QC, QB, QA, nothing change. Still be the same. QA star. Next step, the next value of QA is last QA. Same value of the previous QA. QB star also is QB, QC star is QC, QD star is QD. So nothing change. Then it's hold mode. But if S0 active only, this bit is on right hand side, so this is chip right mode. Chip right means data from QA will shift to QB, QB shift to QC, QC shift to QD. When shift, then it becomes QA at here, QB at here, QC at here. And this person will read data from 0 in. In this case, it's chip right mode. So data will come at here. When you apply 1 at here, 0 at here. Chip right. In, go to QA, QA go to QB, QB go to QC, QC go to QD. And for shift left also, for shift left, S1 is 1, S0 is 0. 1 at here, 0 at here. Now, you will follow this direction. L in, zero input of shift left mode. L in, L is from left. L in, go to QD, go to QC, QC, go to QB, QB, go to QA. If you see this one, it's something like this. this is shift left in this direction. And the last mode of this register that can do is load. With S1 is 1 1 is 1 1. So it rated parallelly from input A, B, C, and D or load, okay, with multiple bit data at the same time. So after clock tick, Q, A, Q, B, Q, C, Q, D will be A, B, C, D, like this. A star become A, QB star become B, QC star become C, and QD star become D. Okay, and for this class, okay, we use this, okay, 194, okay, a lot. So please remember this function of 194. And one thing that very important is about this clear. Here, if you want to clear, you apply right here, okay, to force the output QA, QB, QC, QD become 0. But this IC is asynchronous clear. That means when you apply 0, the output will change to 0 simultaneously. Okay. Okay. Suddenly, when you apply this, okay, all of this, okay, will change to 0 at the same time. Okay. Not wait for clock tick. Okay. Now, the internal circuit is actually it uses multiplexer, okay, to select the input to update internal D flip-flop. For example, if you apply S0, S1 is 0 0. For 0 0, right, this one then become 1 1 at here and 0 0 at here. So for 0 0 is 1 at here, right, and 1 at here. That means this output is 1 1 and this one, and what? And this signal is from what? From QB itself. That means QB data from QB, okay, feed to input of D flip-flop. Okay. So when clock tick, okay, QB will update to QB, so nothing change. That means when S1 is 0 is holdable, nothing change. If S1 is 0 is, for example, is 1 1. 1 1. 1 is 0 0 at here, 1 1 1 1 at here. So in this case, it's 1 at here and 1 at here. So it's not input from B, okay, and to 1 1 is become B at here, okay, and another output of AND gate will be 0. Then data B will feed to this one, okay, for another bit also, okay. For example, A, okay, will flow and feed to this input. That means when clock tick, okay, QA, QB, QC, QD will update with external input. Okay, BC, BA, like this. D, C, E, and A. Flow and update. It when clock tick. Okay, and if you apply, for example, 10, you apply 10, 1010, this one, okay, data from QC, okay, we feed to QB, and QB we feed to QA, this one. From QB. Okay, so this is shift mode. Shift mode. Okay. So for so on also same similar way of shift mode. Shift left or shift right. Based on the value of S1, S0. Okay. Okay, before continue the example, let you remember this one. It's pretty easy. Okay. Based on this layout of IC, the mode is based on the value of S1, S0. Okay, if S1, S0 is 0, so when clock tick, nothing change. Okay, S1 active, S0 not active, nothing change. It's hold mode. But if S1 active early, then we apply 1 at here, 0 at here. So you will use L-in as 0 input. Okay. Feed, okay, from top, okay, to the bottom. QD to QC, QC to QB, QB to QA. But if you apply 0 at here, 1 at here, S0 active. Okay. So data will from Rin. Go to QA, QA to QB, QB to QC, QC to QD. Right mode. And when S1 is 11, okay, S1 is 11, it's load mode. You read data or load data from the CBA at the same time. Okay, it's all for mode of this 164 chip register. Okay, now let's see example. For the example, we use chip register to implement counter circuit. Counter circuit. Counter, do you remember? Counter circuit is the circuit have state machine with single cycle like this. For state change, we change at a cycle. For example, this one. Use this chip register 194 to implement the first counter is ring counter. Assume the initial state is 0001. Define this is maybe LED or lamp. Okay, when clock tick, 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 tick. Okay. The active bit, okay, you shift to the next LED. Shift, and then back to QD again. So this behavior then is called ring, okay, ring counter. Okay, if you want to design this, can you? Yes, right? At first, how many steps of this one? QD, active, only one bit, QC, only one bit, and QB and QA. So there are 4, right? 4 patterns. That means it should have 4 steps. 4 steps. So this 4 step is maybe like this. This is active bit. When clock tick, shift to this one, clock tick, shift to this one, clock tick, shift to this one. Okay. So in general, so let I show you some design. At first, write down QA, QB, QC, QD. When clock tick, change to QA star, QB star, QC star, and QD star. The state, initial state is what? 0, 0, 0, 1, right? And the next is 0, 0, 1, 0, 0, 1, 0, 1, 1, 0, 0, 0, and then back to 0, 0, 0, 1 again. So the next state is what? It's 0, 0, 1, 0. Next state of this is 0, 1, 0, 0. Next state of this is 1, 0, 0, 0. And next state of 1, 0, 0 is 0, 0, 0, 1. 0, 0, 0, 1. Okay. And then now let's observe. Okay. The relationship between Q star and Q. For example, QA star. QA star. The value of QA star 0010, same as QB. And QB star 0100, same as QC. And QC star 100, same as QD. Okay. So the problem is QD star. Oh, QD star same as what? QA. So now you can write transition equation like this. QA star is same as QB, right? QB star is Q0100 QC. QC star is QD, and QD star is QA. So if we use because this IC use DV flop inside, right? So QA star you want to be QB, right? That means you must connect QB to input of QA, something like this. Okay, you use design by using D flip-flop. Is QB connect to input of D of QA, and connect QC to QD, connect QD to Q input of QB, and this input is from external input, is 0 in. And note here from this, actually if you use this IC 194, you can see that before it's shift, right? Shift from QD to QB. QD to QC. QD to QC. QC to QB. QB to QA. And this serial input, of course, for your this mode is must from L in, L is left. So you must use shift left, okay, L in. So you apply 1 at here, 0 at here. It's shift left mode. Now you connect what? Q, QA to QB, QB to QC, sorry, QD to QC, QC to QB, QB to QA, right? And input of QD must be QA. But this IC input read from L in. That means you must connect QA to L in. Yeah, that's all. And for input clear, if you don't use, you apply 1 because this is active flow. Okay. And apply clock at here. Okay, finish. So you can implement ring counter by using this IC 194, like this. Connect like this. Connect to L in. Okay. And in this case, use S1 is 1, right? And S0 is 0 for chip left. But okay, to assign initial value, okay, so you need to reset. In this case, you load. That means if the signal is 1, it's load mode, right? And initial state maybe it want to be 0, 0, 0, 1. So you must connect A, B, C to ground, right? 0. And connect D to 5 volt. So when reset active, the circuit will read data from A, B, C, and D to update 0001 for QA to QD. Okay, that's all. And when you operate normally, you don't reset if this input is 0. So then it becomes 1, 0 or shift left mode. The data will flow with this direction. Okay. Okay. And okay, you can check. For example, if I start from 0, 0, 0, 1, okay, when clock tick, data will flow, right? From L into QD, QD to QC, QC to QB, QB to QA. Basically, this bit will shift to this bit shift to this position, this bit shift to this position. That means you can copy, right? You can copy these 3 bits, shift down 1 bit, 1, 0, 0, okay? And this bit from L in. And now I need 0, right? 0 at here. So that it becomes 0 at here. After that, when next clock tick, this 3 bit, okay, copy and shift down. And this bit now is L in. That means the 0 will update it here. And for the next clock tick, okay, this 3 bit copy and shift 1 position down. And this bit, okay, feed to L in. So when clock tick, this bit is 0. After that, this 3 bit 0, 0 shift down, and this bit, okay, feed to L in. So when clock tick, this bit, this position become 1. Note it repeat, okay, this state 0, 0, 0, 1. So this ring counter then have four states, okay, for this. And please note, if your circuit is lost to some unused state, for example 0, 0, 0, and 0, what happens when clock tick? These 3 bit shift down 0, 0, okay, and read L in to this. It's to be 0, 0, 0, 0 state. That mean this circuit, okay, when the circuit or state machine lost to some unused state, it cannot go back to normal state by itself. You need to apply reset. For example, apply 1 here, okay, to make this circuit, okay, become initial state of 0, 0, 0, 1. And this is to show you some state diagram. For normal state have got 4, and this unused state. Your machine lost to unused state. It cannot go back to normal state, okay, by itself. You need to reset. If you don't want to reset, you want the circuit can correct or can go back normal state by itself, you can do. How? Okay, you just apply this one, this AND gate with active low input. Actually this is no, okay, but you can consider it as AND. This output will be 1 when these inputs, okay, or this bit is 0, 0, and 0. Okay. 0, 0, 0. If it becomes 0, 0, this output become 1. That means when clock tick, it go to 0, 0, 0, and 1 here. So it becomes state of 0, 0, 0, 1. So assume initially the state is something that not normal state. Something. If this 3 bit is not 0, 0, 0, that means this output is 0, right? 0 right here. That means when clock tick, copy this 3 bit shift down, so then it become x, 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 okay, and this input L in, okay, update to this position, then it become 0. Okay. And now assume this x0 is not all 0. That means this output still be 0. So when clock tick, you just copy this one 0xx first. 0xxx and read data from L in. Then it becomes 0 at here. And for the next clock tick, assume x is not 0, right? So when clock tick for the next one, then it's become what? 0, right? 0x. And because this is not all 0, so this bit is 0. That means when update with this condition, then it becomes 0 at here. So now you can take a look that this one is all 0, 0. That means this output then become 1. When clock tick, copy this 4 bit 0, 0, 0, and read data from L in. Then it become 1 at here. So then now it came back to normal state. So this circuit, okay, we just wait for 2 or 3 clock tick, okay, the circuit can back to normal state by itself. This kind of circuit, okay, is called self-correcting. Self-correcting circuit. In this case, is ring counter, so it's called self-correcting ring counter. And this is state diagram. If you want to check that the circuit have got property of self-correcting or not, okay, the one method, okay, you write state diagram. If, for example, if every undo state, for example, is 111, when clock tick, it go to 1110, with this one also undo state. But if you wait for 1, 2, 3, okay, 3 clock tick, it can back to normal state. Okay, so if every undo state, okay, can go back to normal state by itself, okay, it's called the circuit have got self correcting property. Okay, and for this one, the chain, right? This one, active flow input, active high output, chain to active high input and active flow output. Okay, the result will be opposite. There is this one for the normal state. Okay, there is bit 1, only 1 bit. But for this one, there is only 1 bit of 0. Okay. Another one is 111. It's different. Okay. Next, okay, example for chip register counter is Johnson counter or twist ring counter or Moebius counter. Same circuit but have many names. Okay. Let's start from 0, 0, 0, so okay, all off. And when clock tick, 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 okay, LD, okay, turn on, okay, turn on, okay, for each clock tick, okay, by 1 bit, okay. And after that, when clock tick, 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 okay, off, 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 off. Okay, when clock tick on, off, 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 off. Okay, this behavior is called twisting counter or Johnson counter. Okay, so based on this behavior, you can note that, okay, there are 8, right? 8 patterns, namely 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, and 1, 1, 1, 1. Okay, when all of these become active, then the next clock tick, this bit will be not active. 1 bit for the next clock tick go to this state, okay, not active this 2 bit, and then not active 4 bit. Note for this one, if you want to check the state, for example, the circuit, the machine or the counter is on state S3 or not, you might check this bit 0, 0, 1, 1, right? So maybe based on this one, if you check all these 4 bits, you can check by Q3 prime and Q2 prime and Q1 and Q0. Okay, if this condition become true, it should be 1. Anyway, for Johnson counter or with ring counter, note for this state, okay, If this is 0, 0, 0, 0, okay, this is V1, okay. If this is 0, 0, of this will be 1, okay. Continuous 0 before changing to continuous logic 1. So there is no any state that 1, 0, 0, 1, okay, change more than 1 time. That mean you can take only 2 bit. Okay, 2 bit. This is 0, this is 1. So you can show that to this side of this is 0, from this side of bit is 1. So you can take just with this binary bit. So Q2 prime and Q1. For this state S2, you check this 2 bit. Okay, Q0 is 1, Q1 is 0. So it's Q0 and Q1 prime, something like this. Okay, going to be take. Or for state S1, you can take this most left hand side and most right hand side bit. Only this 2 bit. If it's 0, 0, that means this bit should be 0 also. Or this MSB array is 1, 1. That means okay, this internal bit must be 1, 1 also. Okay, this is the for decode or take that this machine is on stage this state or not. Okay, and now how to design this. Okay, let's try to design this one. Okay, let's start from QA, QB, QC, QD. Change to QA star, QB star, QC star, and QD star. The initial state is what? Is 0, 0, 0, 0, right? And then 0, 0, 0, 1, 0, sorry, 0, 1, then 0, 0, 1, 1, and then 0, 1, 1, 1, then 1, 1, 1, 1, okay, before off, okay, 1 bit off at here. For the next clock tick, then it become 2 bit off. And when clock tick, become 3 bit off. And then back to state of 0, 0 again. So let's check how many state. 1, 2, 3, 4, 5, 6. No. Yes. 7, 8. Okay, sorry. 8 state. 8 state. Okay, for Johnson counter. The next state. The next state of this is state of this is what? Okay. 0, 0, 0, 1, 0, 0, 1, 0, oh sorry, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 0, 0, 1, 0, 0, 0, and 0, 0, 0, 0. Okay. Now write equation for each transition. QA star, QB star, QC star, and QD star. Okay. First, QA star. QA star. QA star or something, right? QB star equal to something. QC star equal to something. QD star also equal to something. Okay, what is it something? Okay, what something is, okay, for QA star first, this one, 0, 0, 0, 1, 1, 1, 1. 0, 0, 0, 3 bit 0, 1, 1, 0. Okay, same as QB, right? So, in this case, so then QA star is QB. What about QB? QB star 0, 0, 1, 1, 1, 1, 0, 0. 0, 0, 1, 1, 1, 1, 0, 0. Okay, QC. So, Q, and this one, okay, this is QC. And QC star 0, 1, 1, 1, 0, 0, 0. It's this one, right? It's QD. Okay. So QC star is QD. And how about QD? QD is 1, 1, 1, 1, 0, 0, 0, 0. This is 1 4-bit and 0 4-bit. And there's no right, but this 0 4-bit is 1 4-bit. It's opposite, right? So you can write equation for QD star as opposite of QA prime. After you connect, okay. So for the configuration, choose this one. So you use what? Shift left mode. Okay. Data from LIN you feed to QD, QD shift to QC, QC shift to QB, QB shift to QA. Okay. And from the equation we know that QA star equal to invert of QD star. Okay. QD star equal to qvert of QA. Right? So we just connect inverter and feed opposite value to Rin. So now, you can implement TV string or Johnson cutter, okay, but invert this bit, okay, and feed to Rin. Okay, that's all. At the beginning, if start by clear, okay, then QA, QB, QC, and QD become 0, 0, 0 suddenly. Okay, clear. Okay, by applying 0 here, and then after that, okay, apply 1 here, not clear. And then now consider x1 is 0 is 1, 0, so it's shift left. Data from LIN feed to QD, QD to QC, QC to QB, QB to QA. Okay. And QA now connect to inverter and to Rin. Okay. Okay, now when clock tick, and this at first is 0 right here, right? So this output is 1. So Ln is 1 now. When clock tick, this bit shift down, this bit shift down, this bit shift down, or you copy this 3 bit, right? Down. Then it become 0, 0, 0. Okay? And Ln place to this. When it become 0, 0, 0, 1. And this bit is 0. Okay? Then invert. Then it still be 1. Right? For Ln. When clock tick, copy this 3 bit. Shift down. And Ln 1. Okay? And this bit is 0, right? So when invert, still be 1. Okay? This bit still be 1. When clock tick, copy this 3 bit 110. Okay, shift down and read data from in is 1. Again, this is 0, so output of inverter now is also 1. Then when clock tick, shift 1, 2, 3, this 3 bit, shift down and in, okay, 1, so it's 1 at here. Now it's become 1, 1, 1, 1. Then it's 1 at here when invert, then become 0. That means now in is 0. When clock tick, copy this 3 bit, okay, 1, 1, 1, and in is 0, right? Then shift to here. Now this is 1, so now in is 0. When clock tick, copy this 3 bit 0, 1, 1, and read from in is 0. Okay, after that again, now this bit is 1. That means output of inverter is 0. So in is 0 now. So when clock tick 0, 0, 1, then shift 0, 0, 1 and 0 at this position. For the next clock tick, again this is 1, so output is 0. So shift 0, 0, okay, 1 bit shift and read data from 0, right? Then it becomes 0. Note now the counter, okay? Now back to the initial state of 0, 0, 0, 0. Okay, that's all. Okay, anyway, this circuit, there are 8 states, right? 1, 2, 3, 4, 5, 6, 7, 8, right? 8 normal state. Okay. And some unused state. For example, 1, 0, 1, 0. If the circuit, okay, lost to some unused state, for example, 1, 0, 1, 0, what happened? When clock tick, copy this 3 bit 0, 1, 0, and this one invert, then it becomes 0 at here, then become 0 at here, for example. And then when clock tick 0, 0, 0, 1, 0, 0, 1, this is 0, then invert, then it become 1, 1 at here. Okay, and so on. Okay. Write down all possible state. Okay, you can see that this circuit cannot back to normal state. Namely, this circuit, okay, can do self-correcting. It need to, for example, reset or clear back to the initial state of 0, 0, 0, 0. But if you want the circuit, okay, can do self-correcting by itself, you maybe add this one to check that this bit is 0, 0 or not. Okay, like this. Okay, that this is state 0, 0 or not. Okay, this is S1. When clock tick, it change to 0, 0, 0, 1, right? So from this one, let's check that this bit is 0, 0 or not. Okay, if yes, let what? Load, right? If yes, this output will be 1, and then that means A0 is 1. Okay. It is connected to A0, and S1 already is connected to 5 volt, so now it's 1, 1. Okay. Load mode, so you read data from A, B, C, D, or in this case 0, 0, 0, 1, okay, to update this one when clock tick. Okay. So that means now it can back to this state by itself. Okay. Okay. For this example, you can check by yourself by write down all possible states of this. Okay. And the last application is LFSR counter, linear feedback chip register. Okay, from the previous one, ring counter, there is 4 state, right? And for Johnson counter, there is 8 state. Okay, for 4 bit. Okay, chip register counter. So some mathematician name Carlos. Okay, he is French. Okay, mathematician. He want to generate sequence, okay, of chip register counter with maximum state, okay, before back to the initial state. For example, this one. Okay, this is the feedback equation. Okay, to obtain maximum length sequence. Okay, for example, if you use 4 bit, it's 4 bit, you will check, okay, Q3, Q2 is different or not by using XOR function. If yes, Q0 star is 1. Namely, you feed, okay, the result of these two 0 in. If you use shift left, so that is L in. For example, start from initial state of, for example, if you start from Q3, Q2, Q1, Q0. Okay. Now, if the initial state is, for example, 0, 0, 0, 1. Okay. This is chiplet mode. Okay. So you copy this 3 bit. Chiplet 0, 0, 1. Okay. How about this? This you must consider 4 bit, right? Q3, Q2 different or not? Is same. Then 0. If different, Q star is 1, right? Q0 star will be 1. When this Q3, Q2 is different. Okay, for the next state, again, copy this. Shift left. And then this is same, so it becomes 0 right here. For the next copy this 3 bit, shift left. And it's different, so 1 right here. Okay. If it's same, Q0 becomes 0. If different, Q0 become 1. For the next counting, okay, just copy this one, 0, 0, 1. Different, so 1 right here. Okay, you can repeat this. Okay, 0, 1, 1, 0, 1, 1, same, so it's 0 right here. 1, 1, 0, 1, 1, 0, different, 1 right here. Okay, and so on. So if you use this method, okay, you can obtain 15 state. 15 state for 4 bit. Okay, and one state that is unused state is what? Is 0, 0, right? 0, 0, 0 is unused state. 0, 0, 0 is unused state because when you use this algorithm, shift left this 3 bit and compare this one is different, then it becomes 0. So this circuit cannot back to normal state if the machine or the counter get lost to this 0, 0, 0 state. Well, if I want to insert this 0, 0 state to this, can I? Yes, we can, right? You just construct is this shift left and this is 0. Okay. After that, this is maybe shift left and then this 0, right? Sorry, it's 1. Okay, so it's possible, right? Because this just shift left. Okay, this also shift left. The different only the value at this position. How to get it? Okay, now let's consider this one. Okay, for 4 bit, this is Q3, Q2, okay, XOR together, and use this one as L-in. Okay, this is the normal, okay, normal one. If you want to insert or add state 0, 0, 0, okay, into the sequence, you must connect this part of the circuit. Okay, now let's consider how does it work. Assume now it's state of 1, 0, 0, 0. Okay, 1, 0, 0, 0. So this 3 bit becomes 0. That means this output becomes 1. Okay, and this 0, 1, so it's different. Output, this output is 1. 1 XOR 1 is 0. So now L-in is 0. When clock tick, this 3 bit shift down 1 position and read data from L-in is 0 now, so then it's become 0 right here. And now 0, 0, so this output of inverter is 0. Okay, it's 0. And this is 0, 0, 0, so output this will still be 1. 1 XOR 0, then it's become 1. Become 1. That means when clock tick, copy this 3 bit, then becomes 0, 0, 0, and 1 added here, become this state. And now, when this 3 bit is not all 0, this output then become 0. Okay, 0 XOR anything still be that thing. Okay, nothing change. So after that, the sequence then back to the original one. Okay, so this is a for example of some application of chip register to implement counter. And this kind, okay, of sequence with maximum length, sometimes it's called LFSR, okay, linear feedback chip register. Note that you can use any bit as the output. Namely, if you use this one, is 1, 0, 0, 1, 1. This one also you can use, okay, but just wait for one clock tick. It's 1, 0, 0, 1, 1. Okay, same, right? Same. And you can apply this bit as pseudo random. Do you remember about the last lecture? for guessing game. Let's show you this one. Maybe this chapter. The guessing game that you already learned, okay, from the previous chapter. Something like this. LED will run, right? And the player, okay, try to press the switch, okay, at the same time when this LED turn on, right? Okay. Anyway, if this LED run with the constant rate or speed, the player can guess easily, right? So for the last lecture, we already introduced you for this signal of enable that form LFSR, okay, or linear feedback chip register. Okay, this enable signal we add to this state diagram. Okay, if enable is 1, so go to the next state. If enable is 0, okay, stay at the same state. Okay, this one also enable is 1, go to the next. Enable is 0, okay, still be at the same state. That means if we use this, okay, from linear feedback register, 1 bit, maybe generate 1 0 0 1 1 and something like this, okay, that hard to guess, okay, the next digit. So it's called random, right? Actually, it's pseudo random. So if it is 1, so it's go to next step. If it's 0, become the same state. 0 again, still be at the same state. Then 1 1, okay, 0 stay at the same state, something like this. Okay, so you can use, okay, this you can use this one, okay, to generate pseudo random signal, okay, for the guessing game. Okay, that's all for today.